Hey everyone. So in this video, we're going to be doing monotonic pushovers on the model that we created last time. You may notice I made a few changes to the cross section. I'll get into that in a little bit. The three techniques that we're going to be using for our monotonic pushover is low control of force, low control of displacement, and displacement control with forces. If you've seen my theory video, you probably have a pretty good understanding of how each of these work and a few of their limitations. If not, it's definitely worth checking that out. So yeah, let's get into things, and I will start by sketching an outline of what the structure of our program will look like. So I'll pull up a blank directory. These are all the tutorials. Because we're going to be using the sections I defined last time, we'll copy over the model functions. I'll also copy over the documentation. Really, you won't need this because we already know what's going on, but it's probably a good idea just for your records to have that there. So we're going to have a model functions file. We're also going to have, of course, a main analysis file. So I'll make that. As per usual, we run our main analysis out of this script, and this will call on all of the other functions that we create. I'll also create a function called analysis, or excuse me, a file called analysis functions. Oh, excuse me. Spelling is hard. Analysis functions. Typing's hard too. So this is where we will have our pushover analysis. It's also where we'll have the analysis loops in our file. What else are we going to need? We will need a folder for the recorders. So I'll create a copy of this, and I'll call this recorder functions. This is where the different recorders that we have in our model will be called from. It's probably overkill to have this, but I generally like to have the recorders separated out into its own file, just for peace of mind. So let's see, we have analysis model recorder. I feel like anything else? Oh yes, and for this example, we are actually going to make a few plots. So I'll create a folder called plot functions. And this is where we will call some scripts that we write in matplotlib. We'll also have 3 repositories. Because we're going to be running the analysis in 3 different ways, we're going to want to put our outputs in each of those repositories. So I'll create one for each type of pushover that we're doing. So we'll call the first one pushover load control and force. So this is for the load control of force, and we'll copy this. So we'll also have one for load control displacement, and one for displacement control with forces. And we will save the outputs of our analysis into each of these folders respectively. Start by actually going into our model functions. So I will open up Spider, and I will copy the model functions. So take this, and I'll just walk you through the changes that I want to make to the file. So immediately, what I want to do is I want to take this b value pretty far down. This is not the most realistic value. You can imagine now the behaviors of the material is pretty similar to elastic perfectly plastic. I'm just using this to emphasize some of the differences between each methods. If we have it so that the slope is like a fairly regular slope, we won't see any big drop in our force. And I want to have a big drop in the moment that we have. I also want to change some of these numbers to be a little bit different. So I'm going to change the ultimate to 8 times the yield strain. And let's see. We're also going to change the rebar Y such that it only has negative values. Oh, excuse me. We want positive values, not negative values. Okay. Perfect. So now we should have a section that matches the section that I've specified here. So now that we're happy and we're content that the changes we made are good, let's maybe start in the main analysis file. We'll just do a quick check to make sure nothing explodes when we import these functions and run them. So I'll just copy paste these imports over here. We'll import model functions as MF, and we'll run our functions, the get sections, and what was it called? Build model, and the build model function. Build model. Let's see. Of course, we want to start with a wipe command, and let's run that. We want to spell that right. Okay, perfect. So it all ran. That's great. Well, I'll just do a quick plot. Get rendering. Crap, can't remember what this is called either. It's called model functions. Okay, good. All right. So now we can see the model is set up. If that was too fast, I use Control-G to go to the source of the file to figure out the name of the model functions because I did not remember it. But so we can clearly see our import works. That's all great. Now that we have the main analysis set up, let's do like a quick sketch of what this is going to look like. I'll comment this out for now. So we're going to define some variables, and we're also going to run our analyses. So we'll do pre-processing, and then we'll do the load control with force. We'll create a section for all 3 of the methods that we're going to use. So load control with displacement, and then displacement control with force. And because I have these 3 methods, I probably don't want to be running I don't want to run all 3 analyses every time, all the time. So I will create some variables at the top. So run analysis LCF. So this will specify whether or not we want to run the force, the load control with force. And I'll create this variable 3 times for all of the other possible analyses. So this will just provide us a convenient way of turning on or off the analyses at the top of our file. So that will be useful. Other stuff that we should define the name of the analysis. So we'll say pushover, load control, force, name, and then we'll call it pushover underscore load control underscore force. So you'll notice that this name is specifying to the folder that I've set up, and in the future we're going to use this variable to change repositories. So we'll actually go into these folders. So obviously we're going to want to have one of these for each of the types of analysis. And just copy that guy. And then displacement control with force. Okay, great. So these are the names of our analyses. And before we write anything else, let's see. So a sketch of what this is going to look like for each analysis is we're going to check if the analysis, if we've asked the analysis to run. So we'll go if run analysis and load control force. Oh, excuse me. Let's throw up here. No, that looks good. Equals true. Then we'll do the stuff that we want to do. So, and in this case, we'll want to build the model. Build model. We'll want to run the analysis. And then maybe we're going to want to create a plot of the analysis. So for each one, we're going to have this kind of general structure. I'll copy in the commands to build the model that we have so far and uncomment them. What is it not liking? Oh, this has to be a Boolean statement. So now if we run this, we should have exactly the same thing as before. Of course, we want a wipe command, except it will just be turning on or off the analysis. So if we run it, perfect, you see it works. If we turn this to false and run it, we don't get a picture. So our conditional statement worked. And before I copy and paste this guy to the rest of them, we'll just work on the load control with force for now. So we'll flesh out the functions that are needed for this one, and then we'll make the rest of the functions for the other algorithms, because they'll be pretty similar. It'll just be a fairly quick copy and paste to get those in. So let's start with the analysis functions now. So I'll turn this guy back on to true. We'll do a little bit of cleaning up. I'll get rid of all my sloppy stuff up here. I'm not actually sure we'll have anything in this pre-processing section, but we'll revisit that at the end. So let's work on the analysis functions. We're going to need to import OpenSees at least. I'm not sure if we'll need anything else immediately, so we'll leave that there for now. And I'll just do a sketch of the functions that we're going to need. So pushover, load control with force, so LCF. And let's say that this is going to take one input, and the input that it takes is going to be the displacement. So we will push to this, we'll say maximum displacement, max displacement. So we'll create these functions so they attempt to do the pushover until a certain node that we specify reaches the maximum displacement. For here, it probably makes the most sense to use the top node, so we'll use, say, node 4. And I probably could be more zoomed in, so let's do that. Sorry, guys. Okay. Yeah. Hopefully this will be more clear. So for this load control, we'll first specify a few variables. So as I said, I want to use the control node as 4, so we'll write that. control node equals 4. This is the node that we'll be monitoring throughout the analysis to check if we're done or not. I will use the degree of freedom in the x direction. So we'll write control DOF, control node DOF equals 1. And then we'll say, because this is the load control, I want to have some sort of reference load. So the initial force, we'll say d force equals 1, and we'll make that kilonewtons, and I'll define kilonewtons up here. So newtons equals 1, kilonewtons equals 1,000 times newtons. Okay, so we're going to have those variables. Let's sketch the function. We will define our time series. We'll define loads. Define loads. And we will define analysis options. And then we will run the analysis, let's say. All right, so our program will look something like this. Let's go through the process of defining the time series that we need. So I'll define as a constant time series, just because it's good to have that in the model as your first time series. You never know when you'll need it. Vector. This will be fine. Okay, time series 1, perfect. And then we'll use a linear time series. We'll call it 2. And we will give it a... Actually, I don't think we need any optional arguments. You know what? Let's just be super clear while we're going through things. So I'll take one of these guys and we'll comment it out. Yeah. Okay, so the constant linear is basically the same. So now we need to define the loads in our model. So we'll define certain load patterns. Let's just say we'll scale the load that we apply, and that will be the only load. So we'll have only one pattern. It will be a plain load pattern. And we'll call it 1. And we will link it to our first time series. And do we need anything else? No, I think that's good. And we will define the load now. So load, and we'll be at node 4. So we'll be at the control node. We will have, so it will be d force in the first direction, and then 0 in all subsequent directions. And while I'm doing this, I realize we actually need to have d force be a floating number, or else we'll end up with an error. So we have our loads. Let's just make a call of the function to make sure that nothing is going crazy. Oh, I should define this below down here. Okay, perfect. So we'll call the function, we'll say, I don't know, max displacement will be 1. Doesn't matter right now. Equals 1. And what happens when we call that? Oh, of course, we don't have any models. So in fact, a better way to do this, let's go into our main analysis now, and we'll import the pushover function. So we'll now go import analysis functions as AF, and we will import the function that we just wrote. And now if we run the main analysis, we should be good. If we could spell things. Analysis functions. Oh, and we need to give it a max displacement. We'll pass it 1 for now. Okay, great. So as we go through defining parts of this function, we'll periodically go back to the main analysis and just check and make sure that we haven't made any errors. It can save us a lot of hassle instead of trying to do it all at the end. So we have our loads. We're gonna define analysis commands. For this section, I actually think I'm gonna be a little lazy. I am gonna pull up this model that I created earlier, the basic trust analysis. And I'm just gonna copy and paste in these analysis options. Typically, you can do something like this for most of your analyses. These values generally don't need to be tinkered with too much. I will change some of these. I'll change the constraints to transformation. I will change the system to band general and the numberer to plain. But again, I think these we don't really need to mess around with too much. Next, we will need the displacement increment. So we'll use the normal displacement increment test. As we can see, solution matrix depends on the blah blah blah. Where is it? Basically, this is testing the actual displacement. So it's testing how much the displacement is changing from step to step. And if it's not changing a lot, then we assume that we've reached a convergence. Where does it actually say that? Yeah, usually is equal to the displacement increments that are applied to the model. So obviously, there's a lot of fanciness that can go on, but really what you can think of testing is how much is the displacement in the model changing from step to step. And then if it's not changing a lot, we say that the model has converged. So pull up this displacement increment over here. We'll copy this guy in. So normal displacement increment is what we use. And we will give it a tolerance of 1 times 10 to the negative 8 as a floating point. Take these guys off, and we will let it do 50 iterations. So let's run our main analysis again. We've changed a lot. Great. So main analysis works. The changes that we've made haven't completely broken the model. And I'll add a bit of a comment. So create. All right. So now we're at the actual run analysis section. We'll record the initial state of the model just for fun. So when we look at the recorder files, we'll actually have a reference for the initial model without any loads applied to it. And then we're going to be running the analysis through a loop. Well, let's start off by looking at what the basic analysis might look like. So let's say we want to do something like OK. So OK is the variable that we'll use to check whether our analysis is complete or not, or if it's successful or not. And then we'll do op.analyze and we'll tell it how many times we want to analyze. So if we do analyze 1, then we'll just analyze it for 1 load step. So we haven't actually created any recorders, so we won't have any outputs, but we'll just test what that looks like. Perfect. So actually, there's a bit of a typo here. This should be analyze like so. And because I'm being a little indecisive, I'm gonna change this max displacement to number of steps as follows. So we'll run the analysis for this input amount of steps. What this command is basically doing is allowing us, so if n steps is 300, then we'll run for 300 time steps in the model. Generally, I don't recommend that you run models with this kind of setup. I'll show you in the future a better way of doing this. For this, I don't want to overwhelm you with too much information though. So just keep in mind that this generally is not the way to go about running a model. And in the future, we'll come back to that. But for now, we are finished with this function. We will use it as a template for the other 2 functions. So we'll copy and paste it twice. So this now is the load control of displacement. We'll make a few changes. We'll have this du variable now, and we'll make it pretty small. We'll say it's what is that? That's 1/100 of a millimeter. So yeah, this is probably a lot too small for most applications. Sorry, so we'll define meters above, and we'll give it some units. Yeah, I think this is probably too small for most applications, but it's just kind of what I chose for this particular example. You'll have to figure out a value that works for you and the application that you're looking at. So instead of having this load command, now we're going to have a single point constraint. You can think of this as like a forced displacement, and the inputs for this are a little bit different than the force command. You can look it up, but you can look it up, but I already know the inputs. So we'll give it the control node, the degree of freedom, which will be 1, and the displacement per step. Let's see. Yeah, so this all looks good. So we're done with that function. And then finally, we'll do the displacement control with force. So from above, we'll just take this displacement increment, and we can leave the load in there. But what we do need to change is the integrator. Well, instead of using the load control integrator, we'll use displacement control. Displacement control. And the displacement control integrator, again, you can look it up, but it will take the node that we're looking at, the degree of freedom in question, and the trial displacement per step. And then I'll let it do 10 iterations. I believe this last one's iterations. We could look it up, but yeah. Actually, let's just be super clear. So load control, model commands as an analysis integrator. Okay, displacement control. The last one, yeah, number of iterations. Okay, perfect. 10 iterations. Honestly, we probably don't even need to worry about this. Let's take it out completely. There we go. So the command will look like this. We'll remove the load control, and we should be good to go now. Let's look at, let's go back to the main analysis, and let's now import the analysis functions. So functions as AF, and now we can run them from this command. So we'll go AF load control force, and we'll say, I don't know, 300 steps for this one. We'll similarly do load control. It's better to be, I like this better as a variable. Oh, and oops, I put this in the wrong spot. So, sorry. Let's go to the first section and make sure everything's in the proper section. So, load control force, we'll say n steps. Well, that'll be 300 for the first one. And you know what would be even better is if we create a variable up above, call it n, so number of analysis steps. Yeah, I do this, sorry, the reason why I'm pausing is I do this thing, I like to have capital N for number, but then I also want to have, we'll just do it like this, n analysis steps. So you can see how much I deliberate over the names of variables. We'll say that 300 for the first one. For now, they'll all be 300 actually. Let's make this an NumPy array too, just in case we ever want to do operations to all the elements at once. Anyways, so now we'll input the number of steps as follows. So we'll grab the first element for the first analysis, and we'll similarly do it like this for the other ones. So the reason why I like this just a little bit better is it's kind of cleaner to have all the definitions in the same spot. That way we don't have to go hunting around through our code for definitions that's like somewhere down here. Okay, but yeah, so now we have that set up. We will be good and issue a wipe command at the end of our analysis. You can never have too many wipe commands. The number of times I've been burned for not having a wipe command is a lot. Now we can run our analysis. So let's do that. Let's run our analysis and let's see if anything explodes. Uh-oh. Something exploded. Okay, let's debug. Okay, so I actually figured out what's going on. The program, you can sometimes end up with stuff like this happening. At some point, this value got converted to a floating point value. So I'm just going to issue this integer command, and as we call the analysis, and that will convert the output back to an integer. And then, because obviously when we're issuing the number of steps, we want to have an integer number of steps. And if you don't have that, it's not going to make sense. So now it should run. Everything, of course, fails, and that's perfectly fine. Let's quickly fix, so I issued the same command 3 times. Of course, we want to issue different commands, so load control displacement there, and then displacement control force. So that should be good. We run it again. I'm kind of expecting that the load control up to displacement, that these two later ones don't fail now. But let's just see. Be interesting. Okay, yeah, it looks like now only one of them failed, presumably the first one. So that's good. That matches expectation. So we we now have a model that runs the analysis, runs each of the analyses that we want, but gives us no output. So in order to get output, we're going to have to use some sort of output function. If you go to the Wikipedia, some people like to use these output commands. So you can say, you can get the node displacement at a certain step, so you can record that and store it. That's generally not my preference. My preferred way of doing things is to use the actual recorder command. I haven't stress tested too much, but my speculation is for a really big model where you're trying to record lots of outputs. A recorder command is going to be more efficient than just an output command. But of course, there are going to be for certain models that might not be the case. But my general feeling is if you're modeling something like a building with a decent amount of degrees of freedom, the recorders are going to be faster than using the output commands. That's my feeling. At some point, I'll put that to the test explicitly. So let's go ahead and define the recorder functions now. So if we go over and look at our recorder functions, we're going to want, if we think of the inputs for this file, we're going to want to pass information to the correct directory. We're also going to want to have some sort of analysis name. So if we think of a relative path from the main analysis to the output directory, that path will look something like this. We're going to have, say, we'll say output directory name / analysis name, and then we'll have whatever quantity. So maybe we want the reaction or displacement. I'll just say quantity for now. That's probably spelled wrong. Someone out there knows. I certainly do not. So quantity, and then just to give this a real example, say we want to pass the displacements to one of these directories. The relative file name for that is going to be, say we're doing the load control, so pushover load control force, and then we'll say the base name, so the analysis name will be the same, and the quantity, so let's say top displacement. So this is what that file name would look like. So we need to, if we think of the recorder function, we need to eventually make this file name in order to save the recorder properly. So with that in mind, I will create the function and we'll pass it two input arguments. So we'll define recorder get pushover recorder recorders, and we'll pass it the output directory name, and we'll also pass it the analysis name. So in this case, my expectation, I will just use the output directory name as the analysis name, or rather, the output directory name is kind of the analysis name. But sometimes you might want to have multiple analysis names in the same directory. So I'm kind of just showing this to you because it will work more in general, not necessarily because we need to have a different output directory name and analysis name. But yeah, so then we'll go about creating this portion of the string that we're going to need to pass to the recorder. So we'll say base name, and that will equal the output directory name plus this weird thing that I'll explain in a second, plus the analysis name. So what this is doing is it's creating a variable that contains, like I said, this portion of the file. We need 2 backslashes because if you have 1 backslash, Python does not like that. And it's just how it handles the string conversion. I don't think that's the right word, but internally, if you just have 1 backslash, it treats that almost like a comment. Anyways, so you need to have 2 backslashes to get the output. Then we'll go about creating the recorder. So if we look at the node recorder, there's all these possible inputs that we can pass to it. For our sake, I'll just go through the ones that we need. Generally, you won't need to pass all. You can ignore most of them. So what we'll do is we want to record nodes. So that'll be the first string. Then we're going to save it to a file output. So that's the second part. And then we need a name for the file. So relative to the base, so we're running the analysis in this kind of base directory. Relative, if we want to save it in one of these offshoot directories, we need to name it like as we did above. And so the name relative to these output directories will be the base name plus whatever we are recording. So I'll say top displacement, and we'll give this a underscore as well, just so it's separated. So top displacement, and it's an output file, so .out. And then what else? So we need the time. And what this will do, oh sorry, I should be zoomed in. What this will do is it will save the time step in the file with all of the other quantities that we are recording. Then we will output node range. So this is the nodes that we actually want to have recorded. For the top displacement, we want to record node 4. And I'm kind of arbitrarily choosing the top displacement. You might be interested in something else, so feel free to use something different there. And then the degrees of freedom. So I'll record all of the degrees of freedom, 1, 2, and 3. So X, Y rotation. And the quantity that I want to record is displacement. So our recorder looks like this. Quite a bit going on. I generally like to record more things. Like, I am mostly concerned with the X displacement. So I don't necessarily need these outputs, like the degrees of freedom 2 and 3, but it's generally easier to have them, to ask for like too much and then not have to worry about it, rather than run a whole analysis and then figure out that, oh, you actually needed these extra quantities. So I don't mind asking for a little bit of extra data here. I think that's fine. We do have an error though. I need to import OpenSees. Okay, that's done. I'll take these strings out because I think it's kind of clear what I'm doing, hopefully, at this point. And I will copy the recorder. And So now we'll record the reactions. So I'll change the name. We want to have the time as well. The reaction will be at node 1, and the degrees of freedom will be 1, 2, and 3 as well. And if we want to record reaction, so we'll do it like that. All right, great. So we have our recorder set up. Now we can import it and run our main file with it. Back in the main file, we will import recorder functions. So as RF, and let's call them for the main analysis. So pushover recorders, and because of the way I've defined this function, we can just use the same one for every single analysis type. So let's copy this guy, paste it down here. Load control displacement. All right, and then copy this guy, paste it down here. Load control displacement. So this is displacement control force. Perfect. All right, so moment of truth. Now when we run this, we should see our outputs in the correct folders. So we expect for each folder there's going to be 2 outputs, and we expect that there's going to be 4 columns in each file. All right, let's cross our fingers and press the button. Whew. All right, yeah, that looks good. Okay, perfect. So, yeah, all right. So what's the best way to walk you through this? So let's look at the load control force first. I'll just highlight some interesting things that I see immediately that you may not be aware of or think about. So obviously we look at the load control, and we can see, if you look at the time step, you can see it's doing exactly what we expected. You know, it's increasing by 1 every step. If we look at the displacement control one, we can see that the time step is actually changing. Like, it's not just 1. We can see at the start it's almost linear, and then later on it's changing by smaller increments. Again, this is all kind of completely expected. We definitely expect that because we're using the displacement control, OpenSees is changing the size of the time step. So this is great. We can see the outputs, and really at this point we're pretty much done. Well, like, the analysis is complete. We have all the data we want. I'll just show you how we can actually visualize some of the outputs from our analysis. And then we'll play around with a few of these parameters and do our final roundup. So let's go and create the plot functions now. So pulling up plot functions, I will use matplotlib to do the actual plotting. So it will look something like this. We'll import, and so if you're using Anaconda, you will automatically have matplotlib. You don't have to worry about doing anything special. So I'll import matplotlib.pyplot as plt, and we'll also import numpy. So as you can imagine, we have these files, we have the data in files. We need to actually read that data to understand our results. So we'll create a function that reads the data, and we'll also we'll use that function to plot. But for now, let's just read the data and make sure we understand what's going on. So I'll define a function. We'll call it plot. We'll call it plot pushover. No, pushover, and yeah, I'm just deliberating. That's probably not the best name. We'll let it stand for now. Yeah, and so if we think about the files, we can kind of cheat. We already defined the location, like the name of each file in our recorders. So I'll just copy paste this over here and we'll grab what we need. So I'll pass the directory name and the analysis name, and then I'll also pull out the base name over here. And then we will create a name for the displacement file. So we'll say displacement file name, and we'll use what we passed to the recorder. And then also we'll create a reaction file name. And sorry, I want lowercase for displacement. Alright, so now we don't need this anymore. And we can read the files. I'm going to use a command from NumPy, read text. So read txt. And what is nice is you can actually, if you click on the command to go Control-I, I clearly load txt. Okay, it was load txt. Okay, perfect. Sorry, memory sometimes fails you. So if you go Control-I on this command, you can actually see a little description of it over here, and what like the inputs that it takes, etc. Unfortunately, this doesn't work for OpenSees functions, but for most functions in most packages that you use in Python, you can get a description of the function by going to it's called the doc string. So that's what shows up. If actually, okay, a little bit of an aside. If I go to this function in NumPy now, we can actually see that all this text is just hard coded into the function. So that's actually what we're seeing over here, is the text has been kind of hard coded into that function. But in OpenSees, unfortunately, no one's gone and made these, so we don't have that. Anyways, so we'll use the load text. We want the file name, so we'll pass it the displacement file name, and everything else can stay the same except for we're going to use a different delimiter. So if we look at one of our files, there is a space between each of the numbers, so we'll need to use space as our delimiter. So because I don't trust myself to spell it properly, I'm going to copy paste that in. And we'll give it so just a string with a space in it, and so it knows that the space is our delimiter. And now let's say displacement equals that, and we'll just copy paste it. Do the same thing for reactions. And let's just confirm that our function's working. We'll return displacement and reactions, and let's say let's create just a test. So I'll get the output directory name. Let's try and read from this folder, the pushover load control force. So I'll create a variable with that name, like so. And then I'll just try and call my function with that. So the directory name, and then we've used an analysis name which is the same as the directory name. So if we call this, we should get two outputs. So let's displacement reactions So if we run this, we should get these two variables, and we should be able to see them in our variable explorer. And I'll just also create a print command. So like so. And sorry, I don't know, my brain just I did it up here too. I really having lowercase for like if you have a variable, it's nicer to have that as lowercase. I prefer to have variables lowercase, something like a class uppercase. Anyways, so we run the file. We can see the variables actually do print out. That's great. It looks like everything's set up properly. We can take a look. Our variable appears to be defined properly too. So that's good. We feel confident that our file is reading the values properly. Now we can actually make the plot. There's a lot of different ways you can issue the plot command in matplotlib. I think the simplest, or the way that I use most frequently, is the subplots command. If you think of what this is doing, is this figure, so that we return two objects from the module, and so there's a figure object and an axis object. Both of these have different properties. If you want to say modify a part, like say the limits on your figure, you can do that by issuing commands to the actual axis object. I'm not going to go, in a future video, I'll go deeper into plotting, but for now, we'll just issue a simple plot command. So this is, we will add to our active plot. So what this function is doing is it's adding it to the active axis, which we've just returned with our subplots command. And we will pass in the displacements we want. And before we pass it in, we'll just do some pre-processing. We want the x displacement, so we'll grab that now. I'm using slicing of the variable, so what I'm doing basically is I'm saying for every value of the column and the first column. So if you think of what's going on here, I want just the first column, but I want all values from it. It's very similar to the matplotlib notation, if you're familiar with that. But anyway, so we'll grab the x displacement, and we'll grab the shear force, which will be in the x direction. So define shear as follows. And if you look at the reaction file, you'll note that the reaction is negative because we've applied a positive force. So just to make things easier on our eyes, I'll actually switch the reaction back to positive. Then we can plot it. So we'll issue x and shear like this. Now I feel really silly because I erased the directory name, but let's just test this function by trying to read the outputs from the force file. So I'll type this out again. As follows, and now we'll test the function again. So we'll call it like this. And now when we run, we should see a plot with the quantities that we asked for. So let's test it out. Okay, perfect. Believe it or not, this is actually what we want to see. This just tells us there's some funky stuff going on with our pushover load control model. yeah, why don't I just talk about that right now? So if we look at this file, I think initially it looks like it completely doesn't make sense. And physically it doesn't, but actually numerically it kind of does. So if we look, this is displacement. It's displacing like well over a kilometer. Obviously that doesn't make any sense. Let's just take a quick look at the force control displacement, or the force control reaction, and see if we can just think about what's going on. So we look, the model seems to be doing great until about load step 209. And then all of a sudden we get these massive displacements. So let's just try plotting up to 209 and see what's going on. So I will write so what this is now doing is I'm saying I want every value up to index 209. So let's plot that and just see what that looks like. We see we actually have this pretty nice plot. But what's happening is we're getting to this peak value, and then all of a sudden we're not able to get any further. And I mean, if you recall, this is a problem that we said could happen with the load control command, is we can't actually get past this peak point in a nice, easy way. So if we look at this plot up here, this actually kind of makes sense from that perspective, because we get up to this point, and then things just fall apart. We're not able to actually capture the, because if you think of what's really going on is the concrete is losing its strength, and so the curve will kind of start to decline. But with load control, we can't actually capture that. And then what is actually interesting is this kind of little blip up here. And so might be fun for you to speculate what's going on here. Maybe pause the video or something. What I speculate is going on here is we're actually picking up the rebar fibers. So if you will recall, we had a cross section something like this, right? And we actually had two rows of rebar. So these can carry some of the moment. They can't carry very much, but they can carry some of the moment. So really, this beam is capable of taking, even though the concrete is eventually going to lose all its strength, the steel essentially has unlimited strength because we gave it a bilinear slope with like a really small secondary slope. So realistically, this structure can carry any amount of moment because of the material model we used for steel. So this is what's going on over here, is the amount of load steps that we issued was unreasonable, and it tried to find a displacement that was like way too far. And eventually it does fail because eventually we couldn't reach our convergence criteria with the within that like step. But yeah, so actually I think this is like a pretty interesting thing to see. So numerically this actually does make sense because the rebar is going to be carrying, the rebar has no limit to the amount of moment that it can carry. So kind of a fascinating result, but obviously not a very useful one. So we can go about that if we instead, we'll take out this 290 now, and let's issue a different number of steps to the model. So let's just do 200, and we'll run it over here, and then we will run the plot, and we can see this nice plot over here. So just for convenience sake, let's now let's import the plot function to the main analysis. I will say generally you probably want to have a separate, like a plot script that creates your plots that isn't in the main analysis. You don't necessarily want to be cluttering up the main analysis with plotting too much. But for what we're doing right now, I will import the actual plot functions here, and we'll use them in each with each run to see what happens. So yeah, let's import plot functions as pf, and then I will issue the plot command. We need to pass it the appropriate names, and that should be good. Okay, perfect. So we'll copy this guy in twice. As such. Okay. And now if we run, we should. I'm gonna comment out the plot model command so we don't see these cantilever plots. And if we run the main analysis now, we should see 3 output graphs. So let's do so. Okay, yeah, sorry, I'll clear all my figures just so it's perfectly clear. Great. So we can see we get these output graphs. So this is the force displacement curve. Let's say turn off some of our analyses. Let's turn off the force control. And let's just run this for more steps because really I want to be able to see the deterioration of the curve. So that happened at let's say 10,000. Let's run 1,000. I'm not going to bother doing mental math. Okay, 0.2. So that's right there. So we need 2,000. Okay, great. So we can kind of see the differences between the load control curve and the displacement. If I go to 3,000, we can see that the curve is actually, we're getting this deterioration, which is nice. I'll go to 4,000, and we're starting to get like some pretty sharp drops. I won't push it too far. Actually, this is a, oh yeah, okay, it failed. So I think this is a good example of the, remember when I was talking about earlier that just passing like this number to your analysis isn't great? We can actually get past this point pretty easily by changing our analysis parameters. And in a future video, I'll show you, I'll show the more efficient way of doing this loop. Excuse me, of running the analysis and running the analysis through a loop. But so I think for now, this is where I will leave things off. Let's just so I'll change these values so we can kind of see the results of each analysis method. Clear all plots. So we'll run this the last time. Oh, excuse me, and turn these guys on. Okay, so clear that, run. We can see that actually, as expected, with the load control with displacement, we're able to capture this deterioration curve. Same with the displacement control of forces. And of course, the force control with forces just completely freaks out. Sorry, I should have done one less step. So we're only able to get to this point with the displacement control, excuse me, with the force control with forces. So I think that's kind of interesting to see. Hopefully this highlights some of the things I was talking about earlier. So you might, if you tried using your displacement control of forces, you actually wouldn't be able to capture this deterioration. And like I said, in a future video, I will showcase how we can actually capture more of this model deterioration. Yeah. Okay, so hopefully this was good. Definitely check out those upcoming videos.